we are going to wrap up our section 11.1 topics here with a little bit of proof by induction. We ended our last video discussing the monotonic bounded theorem, which says that every bounded monotonic sequence is convergent. So what this means to us is that we can prove that any sequence is convergent if we can prove that it's bounded and prove that it's monotonic, meaning that it only increases or only decreases. So that really says that we really need to do like two sub-proofs each time we want to prove that something's convergent using this theorem. And it's very common that to end up having to use proof by, or not necessarily having to use proof by induction, but it's very common that proof by induction is an easy access route to proving some of these things here. So we want to do an example of using the monotonic bounded theorem, but before we do that, I figure we should probably talk about proof by induction a little bit more, since even if you guys have seen it, I'm assuming it's been a while since you've used an application of it. So we're going to talk through an example of what does proof by induction do, why does it work, look at a quick example, and then we'll come back to an example about the monotonic bounded theorem. So proof by induction. In general, proofs by induction are used to show that a mathematical statement is true for the positive integers. In general, it's used to show that it's true for all positive integers. We can get some sort of special subset cases there, but in general, this is used to prove that a claim is true for all positive integers. For example, we are going to prove that the sum of the first n integers is equal to the final integer times the final integer plus 1 divided by 2, right? So this is a mathematical statement. We are wanting to claim that it's true for all integer values n. No matter what number n you plug in, I want to confirm that this is a true statement here. So what we don't want to obviously do is just kind of walk on down the line and just attempt it for 1,000 different cases right here, but we should certainly kind of do a little bit of verifying here. And so I'm going to make a little bit of a table here. Always good to explore these things before we kind of get started with them. So if I have an n value of only 1, then our sum is just the number 1. Over here we're going to get 1 times 1 plus 1 over 2, and that is going to be 2 over 2, which is 1. So it does look like these two guys are the same as each other. Remember, we're trying to judge if there's equality between these two columns right here. If n is 2, then we're looking at 1 plus 2, the sum of the first two integers, which is 3. Over here, I'm going to get a 2 times 3 over 2, which is certainly 3. So it looks like that column worked out. We can try this for 3. 1 plus 2 plus 3 is 6. Over here, 3 times 4 over 2 is 12 over 2, which is also certainly 6. And so it seems like, and I mean, I've tried obviously very few samples right here, but at least in n equals 1, 2, and 3, it seems like this statement is true. We want to prove that it is true for all n, not just collect evidence. This is evidence that the statement is true. This is absolutely not proof that this statement is true for all integers n. We would like to prove that. So how are we going to do this? Every proof by induction has two steps. The first thing we're going to do is verify that the statement is true for a base case. In this case, our base case is the n equals 1 case, because that is the smallest such value that n is ever going to take on. We're always going to begin at 1 and add up to whatever our largest value is. So if n were just 1, then we would just be adding, well, we wouldn't be doing any addition, because addition is between two numbers. That would just be literally the number 1 right there, not even any summing to do. And technically, we've already done that. We've shown that this statement is true when n equals 1. When n equals 1, the sum is 1, and this polynomial expression is always equal to 1. So we want to verify that the statement is true for a base case. The second step of every proof by induction is referred to as the induction step. This is going to say, let's show that if the statement were true for the case when we are going up to n, then that proves that it must be true for the n plus 1 case, right? And here's the reason why this is going to actually prove that this is true for all cases for us. We want to prove that a statement is true for possibly an infinite number of possible values of n, right? We can't do this exhaustively by checking every single one. So what we're trying to claim here is that these two steps logically show that this must be true for all possible values of n. Here's how this sort of works. Based on our base case step, step 1, the statement is true for the base case n equals 1. We plugged in n equals 1. We've seen that we got equality. We're verified the base case is true. Based on step 2, our induction step, and the fact that the statement is true for n equals 1, we're going to be able to show that it must then be true for n equals 2. Again, the induction step is to say, assume that we already know that this is a true equality for any value n. We then would want to show that the equality is true for any value n plus 1, that the next case also is good if the previous case is good. Since we've shown that a base case is good, if we've shown the n equals 1 case, then that should validate for us the two steps that are shown at the top of the screen. That should validate for us that the 2 case must be good. Since the 2 case has then been verified, then the induction step suggests that the case of n equals 3 must also work. The induction step will then also say if 3 works, then 4 must work. So the induction step says if any one step works, then the next step works. If we can prove that that's true, and if we can prove a starting case to start from, which is typically our base case, the n equals 1 case, then that must prove that it must work out for all possible values of n, because we've proven that it works for the smallest one, and we've proven that it works, if it works for any one, then it works for the next. So if we can always prove those two things, these are our two induction process, or two parts to the induction process right here, then that will in essence have shown that it must be true for all possible values of n. So this is our 2 steps that are involved in every single proof by induction. The first step is almost always trivially easy. Plug in the easiest number you can into the equation and show that you get equality. This one is almost always incredibly easy. Every once in a while you get some weird special cases of base case, but in 99% of cases, showing that your base case step works out is trivially easy. Showing the induction step is always going to be something that we need to be a little bit algebraically careful with. This is something where I got to say, proof by inductions, I've seen some of these that are so smart and crafty that I can't really believe it. We're going to see in these cases right here, it's not going to be too mind-blowing, but you've got to be kind of smart about how you want to build pieces to show that these statements are going to be true, and you'll see a little bit of that here today. And before we go into our example, I also want to say about some of this craftiness that's associated with the induction step. All we're really trying to do with the induction step is to say if any one case is true, then we've shown that the next case is true. That doesn't necessarily have to be the n case and the n plus 1 case. There are some proofs by induction where it makes more sense to start with the n minus 1 case and then show that the n case is true. That's equivalent because we've shown that for any one case that's true, the next case must be true. I've heard, I've never seen a proof by induction that looks like this, but every once in a while it helps you just to have some different terms to match up algebraically with other terms you have in your expressions. So it's even the case that we could do things like assume the n plus 5 case is true, show that the n plus 6 case is true. As long as we're assuming one case is true and using it to verify that the next case must be true, then that qualifies as our inductive step. I think it's most common to go from n to n plus 1, but that's not a requirement. Sometimes a slightly modified approach will help smooth out the algebra that's necessary to draw the desired conclusion here. So just recognize the induction step is really just assume a given case is true, prove that the case after that is also going to work out. So let's go ahead and see this in action for a very simple example, and then let's return to our bounded monotonic sequence example, which is really the reason we're bringing this up in the first place. So here's the proof that I would like for us to do as our first one here. Right? It's our sum of the first n integers formula right here. So this says rather than actually adding up the first n integers, you could just say that the sum of the first 20 integers should be 20 times 21 divided by 2. It's a one-shot calculation rather than actually having to do 20 operations to add up 21 integers or something like that, right? So this is, hopefully it makes sense to you, this is a very practical formula to have available. It's a one-shot calculation to replace an n minus 1 calculations that you would otherwise have to do for the sum. So let's go ahead and do the 2 induction steps associated with this example right here. The first thing that we're going to do is verify the base case, and the base case here is n equals 1, and n equals 1 is going to show me that the sum from I equals 1 to 1 of I is just 1, and 1 times 1 plus 1 over 2 is certainly 2 over 2, which is 1. And so I'm just going to give this guy the check mark. That just says, yep, verified the base case. I got the exact same number out when I plugged in n equals 1. It looks like this is a true equality for our lowest possible integer input that we could possibly give. And again, I know that n equals 1 is my base case because I equals 1 is the smallest possible value that we can possibly start with here. You should notice that every once in a while we're going to encounter sums that have some very smart, important definition for us that's very helpful, but they're maybe going to start at like I equals 3. In that case, our base case would be n equals 3. It's the lowest possible integer for which this is true. In step 2, what we're going to do here is we're just going to straight up assume that this statement is true. And what we're going to try to show is that this statement where there's n plus 1s in place of n's is also true if this case is true right here. Because again, that will say to us things like, if the n equals 1 case is true, which we already know that it is, this step will prove that the n plus 2 case is true. Now that we know that the n plus 2 case is true, this will show that the n plus 1 case is true, this will show that the n plus 2 case is true. That logic could be processed out an infinite number of times to show that this is true for all possible values of n. So what are we doing here? We are going to assume that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. We want to show. Now all I'm doing is replacing every single n that I see with n plus 1. And we're going to do some algebra and try and get to a statement that we feel very confident in. We want to show that the sum from I equals 1 to n plus 1 of the integers I is equal to n plus 1 times, and now it looks like this is n plus 2 right there because we've added an additional 1 in there. If we can show this equality must be true, then we have proven that the original statement right here in general is true. This is our induction step. So again, we get to assume that this is true. So this is stuff that we can use to, for example, make substitutions in the expressions that we might see down here. So the very, very standard thing to typically do in proofs by induction is to attempt to rewrite your n plus 1 case so that you end up with terms that existed in your n case so that you can make some substitutions. It's a very, very common strategy associated with these guys. So what I'm thinking to myself is, how can I rewrite either the left or the right-hand side so that my pieces will look like the pieces that I get to assume I know stuff about right here? And the thing that I'm seeing right here is that this left side to me looks like 1 plus 2 plus 3 plus all the way up to n plus n plus 1. That's what we really have there for that sum on the left. Times n plus 1, n plus 1 times n plus 2 over 2. Right? And what I'm recognizing here is that n plus 1, technically, whatever, we don't need to do that, put those parentheses there. Those don't necessarily do anything for us for addition. But those do help me because what that really helps me to see is that this is really just this back to being that same sum that we started with before, right? That is just the sum of the first n terms plus n plus 1, right? Because we just added on one additional term that we added on to our sum. And so I think that this might be a useful way for me to rewrite some of the terms of our expression. Notice that we are assuming that our n case is true. So therefore, we are assuming that I know that the sum from I equals 1 to n of the integers is equal to n times n plus 1 over 2. So I'm going to go ahead and make that direct substitution right here. So here, I now am looking at the sum of the first n integers, and I have assumed that it is true that that is equal to n times n plus 1. And we're adding this to n plus 1. And if I can just show that these two things are true, then we're done. That these two expressions are equal to each other, then we're done. So I think all I really want to do here is I'm going to, I guess I want to get a common denominator so I can add this stuff on the left. And I'm going to expand these terms here as well. So I'm going to get an n squared plus n. That's my numerator from the left. Over here, I'm going to get a plus 2n plus 2, and that's all over 2. So notice here, this grouping is just n plus 1. This grouping over here is the original expression that we had on the left. I'm claiming that this is equal to n plus 1 times n plus 2 over 2. And we will be able to very quickly see with just a tiny bit of very simple quadratic math here that we're getting n squared plus 3n plus 2 over 2 is n plus 1 times n plus 2 over 2. And that's true. I can see this by factoring right there. I don't think I need to write one other step. My next step would literally just be to write the same expression 2 times right there. So what we've done here is we assumed that this was true for the case n equals 1. Or sorry, we showed that this was true for the case n equals 1. We then assumed that if it were true for any one case, it's true for the next case. We then showed that the next case must be true, right? It is the case that the n plus 1 case is true if the n case is true, all right? So we assumed this without knowing that it's not, that we don't actually know that this is true yet. But we wanted to say if it were true that this is the case, it should be that the next integer expression should also be a true statement right there. We did arrive at a true equality down here at the bottom. And so again, this is saying we know the n equals 1 case is true. And we know that if any one case is true, that the next case is true. Therefore, with these two statements together, we can logically conclude that since the first case is true, the second case is true. Since the n equals 2 case is true, the n equals 3 case is true. Since 3 is true, 4 is true. And we could logically proceed off to n equals infinity, essentially having shown that this equality must be true for all positive integers n. Right? So we have proven the equality of this statement by induction here. Cool. So we just did our first induction proof. I think this is pretty typically like the bland, most common first induction proof right here. If you want to see more of these, then you should Google for just Google wiki integer sum sequences, and what you'll see are integer sums. Those will be series since they're sums. What you'll see is that there's equivalent statements that look like this for the sum of the first n integers, then the sum of the first integers squared, so like 1 squared plus 2 squared plus 3 squared plus 4 squared. There's a formula for that. There's also a formula for cubes and for fourth powers, and all of them can be proved by induction with some algebra here. So maybe as like if you're thinking that you're wanting to see another good proof by induction, just look up the formula for the sum of the first I squared terms and see if you can work out the algebra that's associated with that guy as well. So let's go ahead and take this proof by induction idea now and come back to our final example associated with this section on introduction to sequences here. And let's prove that a sequence converges using the monotonic bounded theorem. Remember that that's going to require us to prove that the sequence is monotonic, and to prove that it's bounded, we're going to prove both of those things by induction. Once we've shown that both of those are true, we will just be able to conclude that it must converge then, because the monotonic bounded theorem just says if it's bounded, if it's monotonic, then it converges. Right? So we just got to prove two things. That'll give us a third statement of truth right there. Our final thing to remember before I get started with this is that the monotonic bounded theorem only tells us that we converge. It does not tell us what we converge to. But once we know that we converge, then we can use that bit of information to help us solve for what we do converge to. And we'll see that as our very, very last action in this little video here. So also notice we have a little bit different of a case here. This expression has been, or this sequence has been defined a little bit differently than we've seen. This is a recursively defined sequence. When we say that something is recursively defined, that means that it is defined based on its previous term. So notice here that the n plus 1th term of the sequence, whatever it is, it depends on what the nth term of the sequence was. Notice that in our previous sequence definitions, we've been having our sequence sort of like written as like a function, where we might see like the letter n in here, the variable n. But a sub n is referencing a term in a sequence, not just an integer, right? So this is different than the ones that we've seen before, in that our next term is defined based on what our previous term was. And so maybe it's my final statement while I'm talking about this. Notice this entire sequence would wildly change if we changed our starting value right there. If A1 was 3 instead of 2, then every single term in the entire sequence will end up being different, because every term in the sequence depends on what the previous term was. So if we're looking for just the second term in the sequence, it's going to depend on the first term, and so changing our initial value would change the entire sequence right there. So according to the monotonic sequence theorem, if we can prove that the sequence is bounded monotonic, we'll have shown that it converges. We won't show what it converges to, but we'll know it does converge. Our process looks like prove the sequence is bounded, prove the sequence is monotonic, conclude that it converges. And then, as maybe our step 4, attempt to deduce what value it converges to. But that's sort of our like bonus one. Sometimes you can't get that step 4 right there. Actually knowing what something converges to is sometimes a little bit beyond our capabilities right there, but at least concluding that it converges is really the goal of this thing right here. So our first step is to prove that the sequence is bounded. And a good thing to always do here, we want to prove that this thing doesn't just tend off towards infinity, right? So a very typical thing to do, and you should do this all the time, is just compute some early values of our sequence here. So I know that a sub 1 is 2. And let's look at a couple other ones here. So 1/2 times a sub n plus 6. So a sub 2 should be 1/2 times 2 plus 6, which is 1/2 of 8. And that's going to be 4. A3 is 1/2 of 4 plus 6. That's half of 10. That's 5. A4 is 1/2 of 5 plus 6. 5 plus 6 is 11 divided by 2 is going to give me 5.5. A5 is going to be 1/2 of 5.5 plus 6. That's 11.5 divided by 2. That's going to be 5.75. And it seems like what's happening here is it seems like I'm seeing two things that make me feel really good about this. It seems like one, our sequence values are getting larger every time. That's the monotonic part. It looks like it's strictly increasing to me. The other thing that I feel like is happening here is that even though this is getting bigger every single step of time, it looks like it's getting bigger by a smaller and smaller amount every time. It looks like we might not be getting to infinitely large values. Now, if we grew by 2, then grew by 1, then grew by a half, then grew by a quarter, it looks like we're growing by smaller and smaller and smaller steps every chunk of time right here. So this is at least good evidence for me that I feel like it's worth my time to even attempt these proofs right here because, in general, it's not necessarily true that I should say to you, maybe this is my point of graduate school reference for you. Some textbooks that you guys will use when you are in graduate school will say things to you like, prove this statement is true, obviously suggesting to you that the statement is true and that the onus is on you to prove it. Other textbooks will use statements such as prove or disprove this statement. And let me tell you, adding in the words or disprove makes every problem take about twice as long because now you don't know if it's true or not, and the exploration is a required new step for you to even say, should I be attempting to actually prove this and doing a bunch of work, even though it might not be true, or should I be looking for a counterexample, something like that. So prove versus prove or disprove is a world of difference that's out there. Notice in this case, I have told you prove, therefore suggesting to you it is apparently true. If I say prove or disprove, you could just give me one counterexample and call it a day if you can find it. So you'll get to enjoy that satisfaction there when you're in graduate school as well. So we started by looking at the first few terms here. So we want to show that the sequence is bounded. So what are we going to do to show that a sequence is bounded here? Well, let's kind of prove by induction that this has some upper bound. So maybe what I want to do here is compute like a few more terms. I don't know, just to make sure that I feel absolutely good about this right here. A6 is 1/2 times 5.75 plus 6. This will be 11 3/4, and so we should be getting, what, 5 7/8 right there, which would be 5.875. It seems to me like as I'm continuing to walk this guy out here, now I don't trust myself when I want to go to my calculator. Plus 6 divided by 2. It seems to be 5.9375. It feels like this is bounded above by 6. Right. So this is kind of where I'm at right now, is I've done a little bit of exploration, and I feel like I know where we're heading with this guy. It feels like I'm bounded above by 6. So let's attempt to show that we are bounded above by 6. Now, one tiny thing, I want to come back to a technicality here before we move on. Notice that we saw that this is an increasing sequence. And so since this is an increasing sequence, I want to be showing that this guy is bounded above. If this were a decreasing sequence, I'd want to be showing that it's bounded below if we're looking for convergence here. So let's go ahead and attempt to show by induction that our sequence is bounded above by 6. So our step 1 is always our base case. As I promised, these are typically trivially easy. Our base case is that the first term in the sequence is 2. 2 is less than 6. Done with the base case. Step 2 is always our induction step. Assume 1/2 a sub n plus 6 is less than 6. Show that 1/2 a sub n plus 1 plus 6 is less than 6. If we can show that for any one statement, the next statement must be true, then we will have shown that that this is a generally true statement here. Um, and so I'm looking, so I feel like I did something slightly different here in my induction step with this guy right here. Um, oh yeah, okay, no, I'm good, I'm good. So we are assuming, what's the assumed thing right here? That 1/2 a sub n plus 6 is less than 6. What I'm noticing is that this is literally right here, that is what my definition of a sub n plus 1 is. Right, that is my next term in the sequence right there. A sub n plus 1 is this 1/2 a sub n plus 6 right there. So I am assuming that our sequence as it is defined is less than 6. So that's saying that a sub n plus 1 is less than 6. Remember that my goal is to show that this expression is less than 6 right here. And so all I'm going to do is I'm going to try and build this. I've got an a sub n plus 1. I'm going to go ahead and try and construct something that looks like what I want to show. So I'm going to go ahead and add 6 to both sides. And then I'm going to go ahead and divide both sides by 2. And this will be 1/2 of 6 plus 6. And notice that we're exactly where we wanted to be. We're exactly at 1/2 a sub n plus 1 plus 6 is less than 6. We got half of 12 right there. So it looks like we got it with that line right there. Notice also that this is really saying to me that a sub n plus 2 is less than 6 when we really started with a sub n plus 1 is less than 6 right there. So it looks like we have proven by induction that this sequence is bounded above by 6. I showed that the first term is bounded above by 6, and then I assumed that if any one term, and notice I'm really kind of assuming that the n plus 1 term is less than 6 right there, and showing the n plus 2 is true. And that just sort of happened naturally right there by the way that this thing was recursively defined, right? Our formula in this case was always for the n plus 1 term right there. So just based on the way that the formula was written, it ended up being like an n plus 1 and n plus 2 thing instead of an n and an n plus 1 thing. I really just wrote my general statement that a term in the sequence is less than 6, so the next term in the sequence is less than 6 is what we want to show. Realistically, that took us from the n plus 1 term is less than 6 to the n plus 2 term must therefore be less than 6. That still is exactly satisfying the requirements of our induction step right there. So it looks like we have proved by induction. So we've proven by induction is bounded above by 6. All right, so we've done the bounded part. Next up, we want to prove that this sequence is monotonic. And in this case here, remember that monotonic just means it only increases or decreases. In this case, we're looking at an increasing case right here. So notice that this is very slightly different here for our base case. Because to show that something is increasing or decreasing, that is representing a change between two terms. So I really need, I can't just like, I can't just say, for example, a sub 1 is 2. That doesn't help me know that it's monotonic or increasing or decreasing. I need to say, and a 2 we computed as 4. And so I'm going to go ahead and give that the check mark. My base case, my first two terms, it's increased. So I'm good to go right there. Remembering that increasing, decreasing is a change measurement, and change is the difference between two terms. So it requires us to know two terms in the sequence to verify that in the first two terms there was an increase in behavior. All right. So now for our induction step. We are going to assume that a sub n plus 1 is greater than a sub n That's an increase right there. The next term is larger than the previous term. We're going to assume that this is true, and we want to show that a sub n plus 2 must therefore be greater than a sub n. If we can show, a sub n plus 1. We want to start with the change from n to n plus 1 and show that means that it also must be the case that n plus 2 is bigger than n plus 1 right there, the next series of changes that we're going to go ahead and experience there. And so again, I'm just going to sort of build up my pieces, right? I'm going to look for the pieces that I want, and I'm going to build them out of the pieces that I've got. And the pieces that I've got are always the pieces from our assumption. So our assumed statement a sub n plus 1 is greater than a sub n. And what I think I can do for myself is I'm trying to build stuff that's going to look like the recursive definition of our sequence, because I need to beef these up. I don't want a sub n plus 1 on the left. I want a sub n plus 2 on the left. Well, what can I do to show that? Well, I can just build the pieces of our recurrence relation surrounding these guys. It's legal for me to add 6 to both sides of this statement. It's certainly algebraically acceptable for me to take 1/2 of what's going on each side of these statements here. And what do you know? This statement on the left is literally exactly the statement for a sub n plus 2. And the statement on the right is literally exactly the statement for a sub n plus 1 right there. So not too terribly difficult in this case right here. But if you didn't know to do that, that's weird, right? Like the algebra that I just did there is incredibly simple. But if you don't see to like build parts that you want out of parts that you have, it's not necessarily directly obvious what to do. So I do want to say to you guys, like proof writing is the artiest thing in math. I think aside from computing integrals in fancy ways, coming up with ideas for proofs is some of the most impressive things that I've ever seen mathematicians do. So many times where I've beat my head against a wall for hours having no idea what to do, and then go and read some incredibly obvious 3-line proof from somebody else and being like, well, of course that's true. Why didn't I think to do that? That's the soul-crushingly difficult part of grad school right there, is that there's elegance to the way that people put together stuff that looks like this. This case right here I don't think is too crazy, but again, I could totally see it that you guys wouldn't necessarily like see what to do. But again, what you get, the gift that you are given in every proof by induction is your assumption statement, assuming that this statement is true, that the n case is true, or if since we're talking increasing, the n to n plus 1 case is true. If you're not using this piece of information, then you're never going to make it to showing that the n plus 2, n plus 1 case is going to be true as well. So the key to proofs by induction is always strategically using your assumed true statement right here to help construct your next tiered up statement that's going on right there. So proofs by induction provide me a great amount of satisfaction. I feel like they're great. These are really good justifications of us needing to know about algebra, as we saw in our previous example over here. We needed to know a little algebra. We needed to know that we could sort of pick off terms from a sum and then rewrite terms and add them together, do a little quadratic factoring to show that stuff was going to be true. Down here we recognized that there was some algebraic expressions that we were attempting to solve, that we wanted to build things to look like. We had some parts and we built the surrounding pieces so that we could name something else. A sub n plus 1 became a sub n plus 2, right? This is two good proofs by induction here. So we've proved by induction, we've proven by induction. Is a strictly increasing sequence. And what do I got coming up here? Okay, and now I guess let me just do I'll just do that. So based on the work we've done, we can now officially conclude that this sequence for sure converges. We've shown that it's bounded. We've shown that it's monotonic. Therefore, it converges. However, this theorem doesn't tell us what we converge to, just that we converge. We can now use a final idea about the convergence of sequences to help us solve for the value of the convergent limit. So remember that we think that we know what this converges to. I hope that you're all in agreement looking at this with me, that it just feels like we're tending towards 6 here. But man, I gotta really emphasize to you, evidence is not proof. This is evidence that we're looking at on the screen right now. I am uninterested in mathematical evidence from you. I am interested in proof, in guarantees that we know for sure beyond any doubt what's really going on here. So I don't care that it looks like this thing is tending towards 6. Another thing I guess I should say right here is we've proven that this is bounded above by 6. It's totally technically possible that this limit converges to 5.99. Just because 6 is an upper bound does not mean that it is the least upper bound, right? So I know this is going to increase forever. I know that it's never for sure going to get past 6, but I could have probably proven the same statement right here with 7 in that place right there with no issues. I could have shown that this is bounded above by 14, and we would have shown that this is bounded. It still would have proven that we're going to converge, but 14 is definitely not what we're converging to right here, right? So don't overstate what you know. Don't think that evidence is proof. We want to actually prove things are true here. So what's our kind of final sequence idea right here? Well, if a sequence is going to converge to some number L by letting n go off to infinity, by letting the number of terms in the sequence go off to infinity, then it's certainly the case that if we just looked one further term out, if we just looked at the exact same sequence but one additional term out, it's certainly also converging to L as we take n off to infinity. This is really like saying to you, what's the difference between n and n plus 1 as n goes to infinity? And there's essentially no difference between the two. As n gets infinitely large, that 1 becomes trivial right there. So the thing that I know is that our sequence a sub n converges to some number L. We haven't shown what L is yet. I don't know what we converge to. I think it's 6, but I do not know that. I just think that. And so what we kind of know here is we know this converges. We're going to call the convergent number L. And I know that if the sequence a sub n converges to L, then it must be the sequence that a sub n plus 1 converges to L as well. So I'm getting to, I know both of these statements are true. Right? It doesn't matter how many additional terms you go out, one additional term. If we're going to go infinitely far, this guy's going to get to L as well. So what I'm going to do is I'm going to try and use these two statements in conjunction together to attempt to solve for what L must be. And here's the way I'm going to do that. I know another way to rewrite a sub n plus 1. We've been given an expression for that. So I'm going to rewrite this as the limit as limit as n goes to infinity of 1/2 a sub n plus 6. That should certainly, I don't know that yet. That should certainly be equal to L here. And the extra good thing here then is it looks like I can kind of use my limit laws here and say something like 1/2 times the limit as n goes to infinity of a sub n plus, and what are we getting here? This is 1/2 times 6, so that'll just be 3 equals L. Well, the good news for me is I know what this is right here, right? Now I'm going to go ahead and make my substitution in here. That is L. And so now I can just do my little bit of algebra here. I'm going to subtract 1/2 L over to the other side. And I'm going to multiply by 2. And it looks like we now actually know that this does converge to 6. And I proved that because I know that any infinite sequence that converges, it doesn't matter if we include one additional term. We are converging on that value of 6 when we take an infinite number of terms out there. And so again, we play a little bit of algebraic games. We try and rewrite things to make them look like other things that we've got. You should kind of notice here, like, what's really the main algebraic theme of this is like substitution and solving systems of equations in a sense, or rewriting one equation to make it intentionally look like a different equation. This is really algebraic molding. There's a sense that I always like, I know you guys have heard me refer to this as my algebraic beating stick. I think that this is a little bit more like molding clay rather than beating something with a stick. There's certainly times where I'm trying to force things to look like I want them to, but in this case right here, it's a little bit more of a massage than trying to chop down a tree with a baseball bat, I think. So kind of recognize that this is, I hope that you're going to find this chapter is going to make you feel very satisfied in the fact that you're all very good at algebra, and that's actually a meaningful skill to have here in chapter 11 to verify all these statements. So remember to not overstate what you know. Evidence is not proof. Bounds are not necessarily least upper bounds or greatest lower bounds, stuff like that. So this is what I want to talk to you guys about induction here. This was our last example from 11.1. 11.1 is our monotonic bounded theorem example right there, but I didn't want to hop into that without discussing induction, and so I wanted to make sure that was its own little separate thing. I'm assuming that a bunch of you have seen induction, but I know for a fact that a bunch of you have not, and that's definitely a skill that you're going to want in your tool belt. It is one of the most standard tools used in proving things, or at least one of the most easily accessible tools. Lots of other proving techniques are maybe, I don't know, still a little bit weirder out there. I think proof by induction is the most accessible proving technique, and so you should get comfortable with that idea here. Make sure you understand this one. So I'm going to wrap this up by saying I'm going to make a final sort of like bonus video this week because there is an incredibly interesting sequence that's out there called the collat sequence. That has been intensely studied by far the best mathematicians currently alive. There's still some very easily investigatable, but impossibly difficult to answer. I should not say impossible, and incredibly difficult to proof associated with this sequence. And so I want to talk to you guys a little bit about that as well. So I'm going to go ahead and close this video off right now, but I am going to talk to you guys a little bit about our collat sequence here. So I'm going to make one last kind of sort of bonus video here so you guys can see some really cool stuff that is heavily aided by some computer programming techniques as well. So that wraps it up for our 11.1 stuff. You'll get your little bonus video about the collat sequence, and I will see you guys next time.